So we have physics Ph.D. qualifying exam practice problem number 22. So let's begin. Consider a non-interacting three-dimensional electron gas. Part A, derive the zero temperature Fermi energy, E sub F, in terms of particle density. Part B, using the Sommerfeld expansion, derive the leading low temperature correction to the chemical potential, mu of T. For part C, derive the electronic contribution to heat capacity, C sub V, at low temperature. For part D, derive the pressure as a function of density. For part E, derive the entropy in low temperature limit and compare it with the classical ideal gas result. And for part F, explain physically why the heat capacity differs drastically from the classical equipartition prediction. Okay, so this is a Fermi gas and Sommerfeld expansion problem. So for part A, deriving the zero temperature Fermi energy, E sub F, in terms of particle density, we consider a non-interacting 3D electron gas. We include the spin degeneracy, G equals 2. The single particle energy is here equal to p squared over 2m. Our zero temperature Fermi energy at T equals 0. All states are filled up to p sub f. Number of states is n equals 2 times the quantity v over h cubed times the quantity 4 pi p sub f squared over 3. And we're going to use h equals 2 pi h bar. So our n is going to be equal to v over the quantity 2 pi h bar cubed times 4 pi p sub f cubed over 3. So our n is going to equal v times p sub f cubed divided by 3 pi squared h bar cubed. So now lowercase n is equal to capital N over v, and that's going to equal p sub f cubed over 3 pi squared h bar cubed. So p sub f is going to equal h bar times the quantity 3 pi squared n to the 1/3. So our Fermi energy being E sub f equals p sub f squared over 2m. And this would result in E sub f equals h bar squared over 2m times the quantity 3 pi squared n raised to the 2/3. Okay, so that's letter A. Moving along to letter B, let's just go over letter B as using the Sommerfeld expansion, derive the leading low temperature correction to the chemical potential mu of T. So let's see if this holds up here. Okay, so low temperature chemical potential, part B, the density of states, that's G of epsilon equals C epsilon to the 1/2, where C equals V over 2 pi squared times the quantity 2m over h bar squared raised to the 3/2. And that's including that spin degeneracy 2. The number of particles is going to be equal to n equals the integral from 0 to infinity, g of epsilon, f of epsilon, d of epsilon, where f of epsilon equals 1 over e to the beta times the quantity epsilon minus mu plus 1. So using the Sommerfeld expansion, integrating from 0 to infinity, this phi of epsilon, f of epsilon, d of epsilon, that equals the integral from 0 to mu, phi of epsilon, d of epsilon, plus pi squared over 6, k sub b t squared, phi prime of mu, plus on and on and on. So set phi of epsilon equals g of epsilon equals c e to the 1/2. So n equals the integral from 0 to mu of c e to the 1/2 d epsilon plus pi squared over 6 times quantity k sub b t raised to the 2nd times c over 2 mu to the negative 1/2 plus on and on and on. Okay, so from here, n equals 2c over 3 mu to the 3/2 plus pi squared c over 12 times the quantity k sub bt squared mu to the negative 1/2 plus so on and so forth. And at t equals 0, our n equals 2c over 3 e sub f to the 3 halves. Let mu equal e sub f times the quantity 1 plus delta, where delta is proportional to t squared. And expanding this, mu to the 3 halves, that would be approximately or equal to e sub f to the 3 halves, 1 plus 3 halves delta. And u to the negative 1/2, that's approximately equal to e sub f, the negative 1/2 to leading order. Then with 2c over 3 e sub f 3 halves equals 2c over 3 e sub f 3 halves, 1 plus 3 halves delta plus pi squared c over 12 k sub bt to the second e sub f negative 1/2. So from here, we subtract the zero temperature term. So we say 0 is equal to CE sub f 3 halves delta plus pi squared c over 12 k sub bt squared e sub f negative 1/2. And what we're going to do here is we're going to divide by this term CE sub f 3 halves. So we're going to wind up with, after that, is that delta is going to be equal to negative pi squared over 12 times that quantity k sub bt over e sub f squared. So what we're going to get is mu of t is going to equal this, e sub f bracket 1 minus pi squared over 12 times the quantity k sub bt over e sub f squared plus so on and so on. Okay, so that is for part B. Okay, now what we have is part C. Just reading part C here. Part C, they want us to derive the electronic contribution to heat capacity C sub V at low temperature. Okay, so let's see here for part C. See if this holds. Let's change that. Okay, so for part C, okay, sorry about that. So part C, low temperature heat capacity here. Internal energy is given here for U. Let me just adjust this for now. That's U equals the integral from 0 to infinity of epsilon g of epsilon f of epsilon d of epsilon. We're going to set phi of epsilon equal to epsilon of g epsilon equals c e to the 3 halves. And by the Sommerfeld expansion, U is equal to 0 to mu c e to the 3 halves d epsilon plus pi squared over 6 times k sub bt squared times d epsilon of that c epsilon to the 3 halves at epsilon equals mu plus on and on and on. So we're going to get here is u equals 2c over 5 mu to the 5 halves plus pi squared over 6 quantity k sub bt squared 3c over 2 mu to the 1/2 plus on and on and on. So u equals 2c over 5 u to the 5 halves plus pi squared c over 4 times k sub bt squared mu to the 1/2 plus on and on and on. So we're going to use mu equals e sub f bracket 1 minus pi squared over 12 times the quantity k sub bt over e sub f squared, close brackets. We're going to expand to order t squared, where we have the following. Mu to the 5 halves is approximately equal to e sub f 5 halves times that quantity 1 minus 5 pi squared over 24 times that quantity k sub bt over e sub f squared, close bracket. So now from here, u to the mu to the 1/2 is approximately equal to e sub f 1/2. So u equals 2c over 5. E sub f 5 halves minus 2c over 5 e sub f 5 halves, 5 pi squared over 24 times the quantity k sub bt over e sub f quantity squared plus pi squared c over 4 times k sub bt squared e sub f 1/2. Okay, so now the t terms are negative pi squared c over 12 times k sub bt squared e sub f 1/2 plus pi squared c over 4 k sub bt times e sub f 1/2, that equals pi squared c over 6 times k sub bt squared e sub f to the 1/2. So from here, what we have is u equals u naught plus pi squared c over 6 times k sub bt quantity squared e sub f 1/2 n equals, and then from there n equals 2c over 3 e sub f to the 3/2. So c e sub f 1/2, that's 3n over 2 e sub f. So from there, u equals u naught plus pi squared over 6, 3n over 2 e sub f times the quantity k sub bt squared. So u is now u naught plus pi squared over 4n times the quantity k sub bt squared divided by e sub f. And also from there, let's see if this holds. Whoops. Never mind. Sorry about the delay. So also from here, u naught equals ne sub f. So we have the following: u equals 3/5 ne sub f plus pi squared over 4n times k sub bt quantity squared over e sub f. And since that's c sub v, that equals that partial derivative of u respect to t at v. C sub v equals pi squared over 2 n k sub b t over e sub f, or c sub v equals pi squared over 2 n k sub b quantity times the quantity t over t sub f, where e sub f equals k sub b t sub f. So sorry, that's t sub f. Okay, so that's letter 3. That's letter 3. Letter C rather. Sorry, and then part D. We want to derive the pressure as a function of density. So for part D, we want to derive the pressure as a function of density. So pressure as a function of density here. So what we'll do is that T equals 0, U naught equals 3/5 NE to the NE sub F. For a non-relativistic ideal gas, P equals 2/3 U over V. So P naught equals 2/3 1 over V 3/5 NE sub F, and that's equal to 2/5 NE sub F. Using E sub F equals h bar squared over 2m times the quantity 3 pi squared n raised to the 2/3. From there, P naught equals 2/5 NE sub F, or P naught equals h bar squared over 5m times 3 pi squared to the 2/3 times n to the 5/3. And at low non-zero temperature, P equals 2/3 times U over V. So what we wind up getting is here, P equals 2/5 N E sub F plus pi squared over 6N times quantity K sub BT squared over E sub F plus so on and so on. Okay, so that's letter D. Letter E, what they want us to do is derive the entropy in low temperature limit and compare it with the classical ideal gas result. Okay, so let's see if this holds up. If not, we'll just change it, sorry. Okay, so letter E. So low temperature entropy in comparison with classical gas. At low temperature, C sub V equals T times T, that times partial derivative of S with respect to T at V. So this partial derivative of S with respect to T equals C sub V over T equals pi squared over 2 N K sub V times K sub B over E sub F. So integrating from 0 to T, third law gives S of 0 equals 0. Then what we're going to get for S equals pi squared over 2 N K sub B times the quantity K sub BT over E sub F, or S equals pi squared over 2 N K sub B times T over T sub F. So what we could say from here is this is much smaller than the classical ideal gas entropy at low temperature. Classically, many particles can access thermal phase space. For a degenerate Fermi gas, only particles within case of BT of the Fermi surface can be thermally excited. The function of active particles is roughly T over T sub F, so entropy is suppressed by that factor. Okay. And for part F, what they want us to do is explain physically why the heat capacity differs drastically from the classical equipartition prediction. Okay, so here's part F here. Heat capacity differs from classical equipartition. So classical equipartition would predict C sub V equals 3/2 N K sub B for all monoatomic ideal gas. So for a degenerate Fermi gas that T is much less than T sub F, almost all states below E sub F are filled. And due to the Pauli exclusion principle, particles deep below the Fermi surface cannot absorb small thermal energy. And nearby final states are already occupied. Only particles within an energy shell of thickness approximately K sub BT near the Fermi surface can be excited. And building on that here, the fraction of thermally active particles is approximately K sub B T over E sub F equals T over T sub F. So C sub V is approximately N K sub B times T over T sub F. And C sub V equals pi squared over 2 N K sub B T over T sub F. So what we could say here is the quantum Fermi gas heat capacity is linear in T and much smaller than the classical equipartition value at low temperature. Okay, so that's all for this one. Thank you and have a great day.